have been two major ideas within the computing community within the last decade. The first was time sharing, which was being advocated very hard at the beginning of the decade. The key thing that was being observed was that there was a lot better way to interact with a computer. The second major idea, though, of the last decade has been the notion that computer networks were not only needed but were valuable, and they are gradually coming into fruition.
The computer technology has been moving in a way that nothing else people have ever known has moved. Here's a field that gets 1,000 times as good in 20 years. The communication field hasn't been able to keep pace, but the melding of computers and communication and the switch to digital communication technology, aided and abetted by satellites, is doing something pretty good for communication.
The problem is much like small civilizations or small cities trying to develop separately and not having any way of sharing what they learn with other groups. And if that continues to happen, you don't have a civilization. So that the necessity was to provide a mechanism so that what was learned one place could be transferred effectively and directly to other places without redoing it all and learning it all over again at each place. The problems were not in the computers, we found out. The computers could talk to one another, even though they were very different. And time-sharing systems that existed in each computer were perfectly capable of achieving that. The real problem that we found was that the communications was inadequate.
And ideally, what we wanted to do was to use a common carrier offering. Unfortunately, there was no wideband switched common carrier offering at the time.
Our problem at BBN was to build a new kind of digital communication system, employing wideband leased lines and message switching. Message switching is where each path is not established in advance and each message carries an address. We wanted this new communication system to support all the various kinds of resource sharing, which were so important. At the same time, we wanted to build a digital communication system which would stand in its own right as a better, more economical, higher performance, and faster and more reliable digital communication system.
The underlying concept of that network would have to embody the efficient utilization of communication resources, as well as to provide a system which was both reliable, error-free, and provide the high bandwidth needed for interactive use of those resources. This means that users sitting at a terminal would be able to hit a key and see a response virtually instantly, almost as if that computer, wherever it were, looked like it was in the same room. A simple way to interconnect computers and to form such a network is to place wideband leased circuits, in the case of the Arpanet 50 kilobit per second circuits, between each of the computers, and then to interconnect each of the computers to each other to form a fully connected network. As more sites come onto the network, the requirement is then to connect that site to every other one, which means that the extension of the network is just not a graceful thing. And so this naturally leads to the concept of a store and forward technique in order to cut down on the expense of building such a network. And so let's erase these lines over here to leave ourselves for the moment with a loop network which can be extended. And in this type of network, this computer, for example, would talk to this computer not by sending in a message directly, since there is no circuit, but sending a message first to this computer, which would then store it and forward it onto this computer, thereby acting as a relay. In order to have a reliable network of this sort, each of the individual computers must be sufficiently reliable to maintain the kind of communications that's needed. But unfortunately, most computer installations are just not reliable enough, and this leads to the notion of a small mini processor to take on the functions of the computers and to allow a single design to then be propagated among all the installations, so that we would put a little mini processor at each computer, like that, disconnect the 50 kilobit circuits linking the computers themselves, and then interconnect these little mini processors, or IMPs, with the wideband circuits, and interconnect the computers to the imps in this fashion. Now, such a network would then operate essentially in the same fashion as the previous one, with this computer talking to this computer by first sending a message to its imp, having this imp relay it to this imp, and this imp relay it to this imp, and then this imp deliver it to the final destination. Now, this kind of a network can be made to be extremely reliable, since an effective control can be placed upon the design of each of these imps, since there is no large political problem in getting a large number of sites to cooperate in the design and building of the communications part of the system.
We operate a network control center here at BBN in Cambridge, and each imp, every half second, sends us a little message telling us how it feels and how each of its lines are and how each of its hosts are and what kind of loading it's got. And we man that center 24 hours a day, and we use those status reports from the imps to generate statistics about network performance and also to alert the operators to any immediate needs for maintenance, either in circuits or in imps.
Here is an instance of the Arpanet as it was recently configured, as you can see, with some 25 or 30 sites in it. The transmission of a message, say, from a node over here to a node over here might go as follows. The computer at this point would send a message into its local imp, which would break it down into 1,000-bit packets. The packets would then be transmitted from imp to imp along a route selected by the imps themselves. At the destination imp, the packets would be reassembled in the proper order and delivered to the computer. And then a message would go back along perhaps a different route to indicate that the original message was received. The whole transmission cycle typically takes no more than a few tenths of a second. The system is completely independent of the ups and downs of small numbers of lines. For example, if this circuit over here broke in the midst of the transmission, the message had gotten that far, it might then backtrack, go back here, and possibly take some other route until it gets to the destination. There is error checking in between each imp, so that in the transmission from this node to this node, the message that was sent would actually be error checked and an acknowledgement would be sent back, and then from here to here it would be error checked, and if it got correctly accepted, an acknowledgement would go back, and so forth along each set of imps along the path.
A very unusual feature of this system, which I think is quite new, is that it's possible for us to debug any of the running imps in the field. We can actually examine, core, test them, restart them, and even reload the program from our Cambridge location.
In order to add a new resource into the network, such as this, it would get its own imp and would require 1 or 2 or perhaps 3 connections to other imps in the network. That would be all that would be required to effect that connection. So we could, in principle, let's say, get rid of that connection and the network would work, or we could put in that connection over there to add a little more reliability.
As soon as the network began working, we really had a nationwide resource complex. And this resource complex was very attractive to many users who had no resource of their own to really contribute. These people wanted direct terminal access to the net, even though they had no host to get that access through. So we designed a new kind of imp. We called it a terminal interface message processor. We call it a TIP for short. And this machine really includes a very tiny mini host. With this TIP, many different kinds of terminals can be directly connected to the TIP or can be dialed in through low-speed lines to the TIP and can provide access to the entire nationwide resource pool to users at various kinds of terminals.
Let me illustrate such a device down here, which can then be connected into the network. It's nothing more than an imp, and yet terminal devices, some large number of them, can directly connect to that device.
The most immediate cost benefit of the network for a new user is the hardware and resource sharing of being able to get at large computers, time-shared computers, and other specialized computer capabilities throughout the country that meet his needs. This eliminates the need for him to have a medium-scale machine that does everything in a mediocre way.
Specialized hardware facilities tend to be expensive but very efficient. If there isn't any way to distribute their use, to make it available all over the country or all over the world, it may be economically impractical to provide them because there isn't a large enough need for them in any one place. On the other hand, if they can be distributed, then specialized hardware facilities can be very effective and can let us do things that we couldn't otherwise do.
In the case of the large superfiles, the 10 to the 11th bit weather file, which we're putting on the iliac, for example, these would never be available without it being on the network, because it wouldn't be worthwhile for one person to have it all himself.
The thing that makes the computer communication network special is that it puts the workers, the team members who are geographically distributed, in touch not only with one another, but with the information base with which they work all the time. So that when they get to developing plans, the blueprints, as it were, don't have to be copied and sent all around the country. The blueprints come out of the database and appear on everybody's scopes, and the correlation, the coordination of the activity is essentially right there in the computer network itself. And this is obviously going to make a tremendous difference in how we plan, organize, and execute almost everything of any intellectual consequence.
The main point about the data file sharing is that you don't want to update it and maintain it at many places simultaneously. This becomes even very error-prone, if not very costly.
Well, it must be amusing to anyone outside the computer field to watch people inside it rewriting, recreating the same old programs over and over and over. And programs are recreated partly because it's fun to program, but mainly because it's very difficult to get hold of them and use them if they have been programmed a few hundred miles or a few thousand miles away for use on different equipment from that which you have. Now, the network idea makes it practical to use those programs on the machines for which they were written and on which they have been debugged and tested and checked out.
The effect of the network for a user is that now he can start to attack a new problem that he may come up with any resource that may be available within the net, rather than the very limited set of resources available through his local computation center. This has a tremendously valuable effect, because as he starts to look at a problem, he can use any language, he can use any resource. The reliability is higher because he can choose between several machines for a particular run. And his personal situation is greatly magnified into what he can do, because he doesn't have to depend on a very limited set of resources to do the job.
The ARPA network provides a new research opportunity for experimenting with issues in computer-to-computer communication. To make computers talk to each other, a number of functions normally performed by human users must be moved into computer programs. To gain some hands-on practical experience with computers talking to each other, we extended an air traffic control simulator which we had previously developed. Using this as a model, we partitioned the simulation into a number of airspaces. Using the Arpanet as a communication medium, we were able then to couple a number of these independent simulations together, making them talk to each other for purposes of handing aircraft off and for changing flight plans and the like. We are able to dynamically reconfigure one of these multi-computer simulations by ordering the simulation program for one particular area to move into another computer in the middle of a simulation run. The net effect was an ability to conduct a large simulation exercise involving several autonomous programs in several independent computers. We believe that this is an interesting example of future network capabilities in failure tolerance and in automatic load leveling.
One of the things that is coming out as people begin to use the network more and more is that they must have, at the nodes of the network, computers which are of a multix-like class, or essentially a major computer utility, which is capable of manipulating information, because the network itself doesn't hold information, it doesn't keep information. It's an important design criteria, in fact.
Research now going on will someday permit a network user to log in and not really care where his computation takes place. With a distributed operating system, the user will log into a network of computers, the system deciding which computer can best perform his job. This development will make possible much more efficient and reliable use of computers.
Now, the interesting thing is that as time goes on, we find that the powerful nodes also need the network. Because as one begins to take on larger and larger problems, one builds systems which one becomes more and more dependent on, which one must be more and more certain are up and running. And in order to do that, one has to have tremendous reliability against all kinds of catastrophes.
The user of distributed operating systems will know a new kind of reliability. For example, his files could be backed up on more than one site, so that if one of the sites should go down, he could obtain his files from another site in the network.
I'm involved in the ARPA program to develop a speech understanding system, and I think that that program illustrates some potentials of the network. This is a program that involves, at the present time, 8 laboratories. Some labs will develop some subsystems and others other subsystems. Maybe 2 or 3 will develop entire speech understanding systems, but even then it's unlikely that one of them will have the best of everything. There's also a need for a database of controlled and well understood speech samples for use in development and in testing of the various subsystems and overall systems. And finally, there's the requirement that the people involved in all these projects communicate with each other.
The Network Information Center, which is located at Stanford Research Institute in California, sees the network as this multi-leveled experiment in resource sharing, where the resources available are people, computers, data. At one level, you've got the technology that's implementing the network, the circuits that send the bits from place to place. At another level, you've got the protocols and procedures that allow data to be shared, computers to talk to each other, and so forth. And at other levels, you've got the facilities which allow people to get together who are geographically dispersed and allow them to work together and find out information, resources, and so forth that they need to do their job and bring them together. So we see our job as twofold. One, to provide information about resources, about people, about the network that people need to bring these things together to do their job. And then once they've gotten together, these things, particularly groups of people, we'd like to provide services that will aid their collaboration and their working together.
The success of a network will depend by and large how the user views it. You have to give the user something more than he gets at the present time, otherwise he's not going to be particularly interested in the network, and there are lots of political problems associated with that. He presently has a computer center. The computer center, by and large, provides some kind of service for him. The people who run the computer center are going to continue to want to operate in that mode. As far as the economic aspects are concerned, various computer centers would presumably become expert in some area and provide some kind of resource that would be useful to all the others, and they could concentrate on it. They wouldn't have to cut across the whole board and spread out their efforts among many, many different kinds of programs.
The ARPA network has been criticized as not being typical of what's required for a real commercial network. Well, let's look at what present-day commercial networks do. First of all, they're only built by very big companies who can afford the expense of the design and the long lines and so forth. And secondly, they're built around special applications. This scheme of private purpose-built networks is, in my view, a completely false idea of what the future of data communication will be. It seems to me that data communication for a company must evolve in the same way that the company evolves. Organizations change, they merge, they introduce new services, so that in principle every terminal on the network, every computer in the company and the computers of different companies all have to be able to interconnect. This means that the subscribers of the network are a great variety of different terminals, quite unlike the telephone network. And to my mind, this implies the packet switching principle. It requires that the terminals interconnect at the level of messages and not at particular speeds. Well, clearly a public switch network is needed, and I don't think many people would now disagree with this. but it must be very versatile and able to connect terminals of very widely different types. In my view, the communication and the computer people haven't yet really begun a proper dialogue. They're not yet speaking the same language. The thoughts of the communication people are still rooted in the technology of the telephone network. And I think it's necessary, very necessary, for computer people in the future to learn more about the problems of these networks, so they can really join in this dialogue, and in this way we can get the kind of data network that we need.
Well, it's been hard to share information for years. The printing press, of course, was the great step into sharing information, but the printing press didn't essentially handle the problem of distributing it. It handled the problem of copying it. And we have been needing for a long time some better way to distribute information than to carry it about. The print on paper form is embarrassing because in order to distribute it, you've got to move the paper around, and lots of paper gets to be bulky and heavy and expensive to move about.
There are 90 million checking accounts in the United States. These are in some 13,000 banks. And on the average, there's a check written on each one of these accounts every business day. About 100 million checks every business day. And that's 100 million pieces of paper.
If we get into a mode in which everything is handled electronically and your only identification is some little plastic thing you stick into the machinery, then I can imagine that they want to get that settled up with your bank account just right now and put it through all the checks, and that would require a network.
And we have our own network, which links the Federal Reserve offices, there are 37 of them, and they in turn are linked with commercial banks in their communities. That linkage is not yet complete.
The kind of communication required is exactly that provided by a computer communications network. The kind of communication in which you can get in for a tenth of a second or for a hundredth of a second or a thousandth of a second, do your job and be over with it and let somebody else use the facilities.
There is some resistance to changes in people's money habits. Many people like to get currency. They like the feel of it. Other people don't like to have this mechanized and made a matter of record on a bank account because a husband doesn't want a wife to know, what his income is.
There isn't any real need to change things just for the sake of changing, but I tend to believe that things are going to be considerably better for a lot of people when and if we ever get changed over to an essentially electronic base. It's just fundamental that if one wants to deal with information, he ought to deal with the information and not with the paper it's written on.
The network now costs us 1/10 the cost of mail for moving paper, and this cost will continually go down as labor costs go up, so that it's quite clear that material will be moved and handled and stored in computer systems rather than in filing cabinets.
Right now, it's possible to buy for about $1 million an information store that will hold the equivalent of about 100,000 books. So one can buy the store for a book for about the same amount as he can buy the book, so that if everyone had a display console in his home and in his office, he could be reading from electronically stored information instead of from a book. And the difference is he could have access to anything he wanted to read instead of just what was within reach. Well, it turns out to be surprisingly inexpensive if you get wideband transmission facilities to send the stuff right when it has to be read, instead of sending it to a local bookstore or local library in the hope that it might be read.
The network experiment, to be successful, has got to include more than just the technology of getting computer A to talk to computer B. It's got to include the human institutions that will bring together these resources and people to solve real problems of real people.
The processing and distribution technology and the storage technology are going to make it possible to get over onto a new technological base for intellectual efforts before our ponderous social processes will let us. I think more people ought to get in there and think about the social processes.